Let me briefly walk you through the systems of algebraic equations, linear algebraic equations. So let me go back to my notes. So solving a system of algebraic equations. So my algebraic equation, linear algebraic equation, the system of those is given perhaps in the form like this. There are n of them. Okay. This could be rewritten in a matrix vector form. So if you define matrix A as A11, A1M, AN1, ANM, this is going to be my n by m matrix, vector B, B1 through Bn. This is going to be an n-dimensional vector. And if I define a vector of unknowns, call it x capital, which consists of the unknown variables x1 through xn, I can rewrite this equation in a very compact and elegant form, such as a times x is equal to b. Okay, let's call this expression star, this equation star. You probably remember from your linear algebra class that this equation has solutions if and only if the following condition holds. Rank of A is equal to the rank of an extended matrix A augmented by the vector B. Okay? You can verify this every time you have to solve the system of linear algebraic equations, but maybe you don't have to do this every time because MATLAB will tell you if the solution does not exist, the MATLAB will tell you. If we are dealing with a square matrix, if A is n by n and rank of A is equal to n, then there exists a unique solution. To the equation star. Okay? And that solution is given by A inverse times B. Okay? Now, in case of a non-square matrix, if the number of equations is less than the number of unknowns, then MATLAB will solve this symbolically, this system. So let me show you how. Let me show you one by one. Okay. So solving systems of linear algebraic equations. Well, let's start with the square matrix. So my square matrix A, my vector right-hand side B. We're going to solve this system of linear algebraic equations. Ax is equal to b. We know the explicit formula, so x is going to be equal to inverse of a times b. So I'm going to show you various ways of computing. So let me comment this out first. Various ways of computing the inverse of a matrix. So one way is to declare that inv of a times b. Another way is you can do this, a taken to the power of minus 1. You can do this command called lin solve. If it's lin solve, MATLAB knows automatically that we are talking about the system of equations a times x is equal to b, and it's going to give you the answer. Backslash a backslash b, that means a inverse times b. So all kinds of various ways of computing the inverse of a matrix. If you run all of them, you can also verify that you indeed got the correct answer by putting together a times x minus b. If x is the solution to our equation, then this expression should be equal to 0. So every time you can verify that this is indeed the case, but you get the same, with all these different methods, you get the same answer. Okay, so it's the same answer as this, same answer as this, same answer as this. Okay, so that's that. You can also, let's utilize another command called solve. Solve will help you solve the systems of linear algebraic equations as well as nonlinear algebraic equations. So let's see. Oh. Let's comment this one. Okay. Okay, so using solve, we can do the same thing, but using the solve command. Know that solve attempts to solve the system of equations symbolically, as opposed to another command which we'll talk about a little bit later called fsolve. Fsolves looks for the solution exclusively numerically, but solve command will try to find out the solution symbolically, especially in cases when the number of equations is less than the number of unknowns. So the number of unknowns is greater than the number of equations. In this case, you can express some variables in terms of the other. So as a result, the solution to this system of equations will be symbolic. Command solve can handle this. So let's try to do that. So we are talking about the system. Let's say our matrix is square for now. We are talking about the system of three unknowns, x, y, z. We are defining the equation like this, and when we put this into the command solve, MATLAB knows that it needs to find the solutions to the equation when this EQN, the equation defined as EQN, is equal to 0. Okay, so MATLAB will know that automatically. So as a result, what I define as sol, it's going to be a piece of data that contains the solution. In order to extract that solution, you would have to type up something like this: sol.x, sol.y, sol.z. Okay. So, and if you run this, okay. So yeah. So let me run this one more time. Okay. So here's my solution. So remember, I defined my solution vector as sol.x, sol.y, sol.z. So that dot x, dot y, and dot z help extract the values of the solution from that data piece called sol, which is obtained by applying the command solve to the equation that we have defined earlier. So we got the solution. Now you might as well verify that you got the correct solution. So you do the a times x, which is in MATLAB language a times that solution vector, minus b. That whole thing better be equal to 0. And indeed it is equal to 0. How to handle non-square matrices? So as I told you earlier, MATLAB will, the solve command will solve this system of equations symbolically. So I'm defining a 2 by 3 matrix. I'm defining the vector b, which is two-dimensional vector. My variables are still going to be x, y, and z, and I'm looking for the solution a times that x vector minus b is equal to 0. I'm applying the same solve command, But here I have to, since I have more unknowns than equations, I have to define what my variables are. What my unknowns are. So if it's x and y, then z is going to be viewed as a parameter, and the solution to this system will be expressed in terms of z. So if I do that, then sol x and sol y will be expressed in terms of z. So let me see. So this is my x, and this is my y. So both of them are in terms of z. You can do the same thing with other variables. So let's say my unknowns are x and z. In that case, the solution will be expressed in terms of y. You can see that both x and z are expressed in terms of y. And finally, in terms of x. Okay, so y and z are expressed in terms of x. So this is the advantage of the command called solve, which means that it first attempts to solve symbolically, and then if the number of equations is the same as the number of unknowns, so you have a square matrix A, in that case it has no choice but to find a numerical solution. But at first, by default, it will attempt to solve the system symbolically. Okay, and I do have the last piece that I want to show you. Solving parametrically defined linear systems of equations. So in some assignments, you might have to solve the system of linear equations which depend on a parameter, and that parameter may change, may take several values. So for one value of the parameter, you would have to solve the system, obtain the solution. For another value of the parameter, you would have to solve the system, obtain the solutions, and so on. How to do this in the form of a for loop? So let's take a look at it. I'm defining my symbolic variables x, y, z. Here's my system of equations. Okay, so first of all, my parameter is going to run from -10 to 10 with the step 1. You can define it any way you want. So, but A is the parameter. And then I'm going to run the for loop with the internal for loop index I running from 1 to the length of the vector A. Here I'm defining my equations. And then there are various ways of defining the equation, but that's just one of them. Implementing the solve command. So solve is going to solve the equations such as equation 1 is equal to 0, equation 2 is equal to 0, equation 3 is equal to 0. Now I'm extracting the solutions, okay? And I repeat this as many times as the number of entries in the vector A. If you need to plot the migration of the solution with respect to the value of the parameter, you can do it this way. So when you run this for loop, you are building a vector of data for the solution for x. So that's why you're saying x sol sub I. Okay, so this is going to be the solution for x for the index for the parameter a sub I. Okay, and then you're building that vector, and when you come out of the for loop, you're going to have the array of the values for a and the array of the values for x, which is the solution. Same thing with y, same thing with z. And you can plot them separately on different figures. This is going to be like this. Or you can plot them combined all together. For that, you need to use the hold on command. So either way you want. So if you run this, so this is going to be a versus z. This is going to be a versus y. This is going to be a versus x. And this is going to be all of them together in one figure. And I put the legend so that you know the distinction between the lines. You can see that the granulation is a little bit too high. If you want to get a more smooth graph, you can introduce more data points in this vector A. Let's say the step. So A runs from -10 to 10, but with the step, instead of 1, you take the step a little bit smaller, maybe 1/2, maybe 0.2. Let's say 0.2. It will take a little bit longer, but let's see. Takes time. There you go. Oops, I made a mistake. I did not close up those figures. Let me run this one more time so that you can clearly see that the lines are a little bit smoother. Not a little bit, but much smoother, because you're taking 5 times more points. All right, so let me show you that right here. So you see the sinusoidal line is much smoother. But again, this is something that you define yourself. All right, that completes this module.